Hello, everyone. So for those who don't know me, my name is Dr. Clement Chumesi. I'm a medical statistician for the Norfolk Department of Medicine at the University of Oxford. So for those who've not watched the previous video, this video is just a continuation of the previous video on cracking complex research problems using advanced regression, where we were diving deep a bit into forensic investigation based on empirical data. So if you've not watched the previous part or the previous video to this one, please kindly watch that before you progress with this so that you actually will be able to follow what we were doing. Thank you very much. I hope you enjoy it. Please, if not subscribed to the YouTube channel, kindly subscribe and share with your colleagues. Thank you very much. Cheers.
You notice that there's also something called stepwise regression. Like stepwise regression helps you to choose the best subset of variables you should use, okay, after you fit a model. But to do stepwise regression, you have to consider all the predictors. And then once you fit the model, you notice that when you fit the model didn't identify any significant predictor. All the p-values are greater than 0.05. So there are no significant predictors based on the full model. But when you now want to do stepwise regression, you bring something called step. Step, then you specify the name of the model, okay? That would consider the model in different stages. So it's here is the full model. And then this is where it took some of the variables out. And here it took another variable out in sequential fashion. And it will do it till the point where it cannot take any variable out again. So stepwise regression ended at this point. It considered muscle mass, BMI, wound size, wound length, and the victim age as the variables you should rather use to fit your model. That is to say, these are the variables that will give you the best model according to the stepwise regression. We will try and see whether it is true and compare it with the lasso. Okay, so that is what is suggested. And then we'll try and compare it with what Lasso also recommended. Okay, so if the ridge regression, and the stepwise regression concluded muscle mass, BMI, and weapon length and age as the best, these were the best. And the reason why these are the best is because they are the models that give rise to the least AIC. So in regression perspective, there's something called model selection criteria. So we have AIC's archaic information criterion, and we also have BIC, Bayesian information criterion. It will fit two models of the same kind. The model with the least AIC is considered as the best model. Okay, so you notice that as it reduces the full model, the AIC was 24. But as we were reducing the model, as it was removing unimportant variable, the AIC was improving, meaning it was getting lower. So it got to a point where it considers there's no need to further remove any variables, okay? And that is something we need to. So that's what we mean by the step function. There's also a certain function called drop one. So if I should replace this step with drop one, it will also tell you all the predictors. If I drop a particular variable, how does it affect the AIC? So for instance, let's say this none is when we've not removed any predictor from the model. This was the AIC. So this one is telling me, okay, if I remove muscle mass from the model, the AIC will rather increase, means if the AIC will get worse. That means that muscle mass is quite important. I don't have to take it out. If we look at BMI, here it's telling me that if I should remove BMI, the AIC would reduce to 22. That means that the AIC would even get better than it was with when I considered all the important selections that the stepwise concluded. Okay, like look at weapon length. If I should remove it from the model, it would increase the AIC to 210, something which was 24. This is to say, this is very important that when we take it out, it makes the model very worse. Okay, so these are some of the ways to interpret. So the drop one can be very important. So here, although BMI was selected as a good predictor from the stepwise regression as in the final model, like muscle mass, BMI, wound size, and wound length, this is telling me that if I should take away BMI, I'm going to get a better model than if I keep it. Okay, so that is just something it's just a pointer. So here, what I decided to do was that I fitted the model based on all the predictors that the stepwise regression concluded. Stepwise regression concluded on these ones, okay? So I fitted the model based on what it concluded. Okay, someone is asking a question. Okay, please, I'll answer your questions in the chat after we are just wrapping up. We are almost done. So once we are done, I'll take every question you have. Okay, so here I fitted the logistic model based on the selection stepwise gave me. And after fitting the model, you notice that it didn't conclude on any predictor as significant. Did you notice that here, if I take BMI out, it will improve the model, reduce the AIC. Now look at something. I decided to take even not only BMI. Here I decided to take what out? I decided to take the victim age. Look at the victim age. The victim age here, if victim age is taken out, okay, the AIC was also worse. But somehow, when I took away the victim age, even though victim age was recommended by the by the stepwise regression, you notice that it now made other variables to be significant after taking it out. So the take-home message here is that the instances where you do a regression analysis, some of your variables are not significant. Maybe it's because of just one variable that is causing everything else not to be significant. And maybe that variable was not even important in the first place. But why should you have it there if that is causing variable that are supposed to be significant to be insignificant, right? So these are some of the modeling considerations. So it meant that the moment, let's say, lasso regression makes selection for you, those selections are what Lasso believes is good. It doesn't mean that use all the ones it has said. It means that the ones it has said, you can check which subset of it or whether all of it or which subset of it will get you good results. Okay, so that is why when you make a model-based decision, also always have control. Okay, always have control by also checking whether the selection it gave is indeed good. And if I should take something out, does it even help me improve significance and so on? Fine. Okay, so now look at it carefully. This was what Lasso gave me. The Lasso told me to select muscle mass, BMI, wound length, and wound size, and the rural whatever as the best predictors for the model. And you notice that range regression also told me muscle mass, which Lasso concluded. BMI to Lasso concluded. The wound size to Lasso concluded. The weapon length Lasso concluded. But the only thing that the range regression did not the stepwise did not conclude. Sorry, was the urban or rural area, like the location. It didn't conclude. And notice that here Lasso did not select victim age, but when we did the range regression, it selected victim age as important. Okay, so this is what the stepwise regression selected. These are the important variables, the important predictors it wants us to consider. Okay, but Lasso gave something similar. There's only one variable that changes from both ends. Lasso concluded on everything up to this point, but didn't select victim age. And then range regression, range regression included victim age, but did not include the location. Okay, so that is something we should just bear in mind. Okay, so now we are also fitting the model based on the Lasso. You notice that when you fit the model based on all the options Lasso gave, we automatically still see significance. But when you fitted the model based on all what the stepwise regression did, we didn't see any significance until we choose to take something out, until we choose to take one of the variables out before we saw significance. But you notice that for the Lasso, the moment we included all the things it suggested, we were able to achieve significance. Okay, so it was able to conclude muscle mass as significant, the wound size as significant, and then the weapon length as significant. It didn't conclude BMI and rural areas as significant. When you have this kind of results, when you're doing regression, the ones that are not significant, there are instances where a variable is not significant. But when you take it out, it will cause a certain variable that was significant to be insignificant. And when it happens that way, this introduces us to another concept called moderation and mediation analysis. So when we say a variable is a mediator is like a third variable that in its presence, it causes a certain predictor to have a significant effect on the outcome. If that variable is taken away, that predictor will not be significant anymore. So it meant if you had a certain variable that was not significant, like a certain predictor, it didn't have any significant effect on the outcome. But when you added a certain third variable, it caused that previous variable that was not significant to be significant. It meant that variable we added, the third variable, might be, we are not saying it will, but might be a mediator, because mediators, they cause variables that are not significant to have significance in the presence of a third variable. In essence, it means that a third variable is causing them to have an indirect association with a dependent variable. So that is what we mean by mediators. And we have something called moderators. For moderators, these are also third variables that in their presence, it can first of all increase the strength of association or even change the direction. So for instance, this one, you are seeing that it has a negative relationship on the outcome. And if there was a certain moderator and we added it to this model, it could have changed this negative to positive. Okay. And if, let's say, the overall model, the predictive performance was, let's say, was good, but when we add that moderator, it can either makes it better or worse. So these are something we just need, but it falls outside the scope of this presentation. I think I've covered them on my YouTube channel as well. Okay, so now what we've just done is, so far, summarizing what we've done so far before we wrap up, we are almost there, is that we have now looked at how to import data into R. And after import, and the data can be any data type. We say just have to set a working directory, and then you go and check the name of your data. Always convert your data to CSV if it is in the Excel format. But if it's in Excel, convert it to CSV before you import. In that case, you don't need a package to import. If the data is in SPSS, SAS, Excel, or any other format, then you need a package to import. I've already covered how to do that on my YouTube channel, so you can always visit that. So at this point, if you have data in SPSS, Stata, you should be able to do the analysis in R, okay, by just importing that data set. And everything will be like you've just imported any data into R. Fine. And now we've said that before we fit the model, we need to split the data into training and testing. And we are using the training data to train the model. By training the model means we need more data set for that. That's why we are using high percentage of the data for the training. And for the testing, we are not using it as part of model fitting. But what we are doing with the testing is that we know the true values of the weapon types in the testing set. And we are going to now use the fitted model to predict those weapon types based on their predictor information. And based on the predictor information of the data we left out, we will now try and predict the weapon type and compare the proportion of times the prediction agreed with the true values. Okay, and that is how we quantify accuracy. Okay, and to do that too, we said we have so many. We had about 10 predictors, and not all the predictors are important. And we noticed from even the correlation matrix plot that there was high correlation among some of the predictors, contributing to problems of multicollinearity. So in essence, we needed to now identify which subset of predictors among the candidate of predictors should we use, okay? And we suggested that we should use a lasso regression because it's able to take away all those variables that are not important and eliminate multicollinearity. The stepwise regression does a good job, but at the end of the day, it is not very good in handling multicollinearity. Okay, and we've learned the effect of multicollinearity. So now we notice that after the stepwise made a selection, it didn't achieve significance in any of the predictors until we decided to take one of the recommended variables out before we saw significance. Okay, but with the lasso, all the ones the lasso suggested, once we include them, we're able to get significance even without taking anything out. But at this point, the ones that are not significant, it is a good modeling practice to check if we should take them out. Does it affect the significance of the other variables? So for instance, why BMI was not significant and why I think it should be taken out. Even from the stepwise regression, we notice that when you take it out, it makes the model better. But here you could also note that BMI has a high correlation with muscle mass. So somehow, I'm not sure why lasso kept BMI, but you notice that it took away the perpetrator height, which had a high correlation with muscle mass and BMI. So it took that one out. and kept BMI. But I still believe that, as you can see, BMI still have high correlation, and it's not even significant. So why should we have it there? So at this point, you then add this is why we call adding expert. So we've done a model-based decision. Now you have to make expert decision. So from my expert decision, BMI is not significant, and somehow I was having high correlation with muscle mass. I'm going to take it out, and I'll check if I take it out, does it affect the significance of any of the variables? If not, then it should be out. And then if you look at the location too, at this point, it's not significant. So if I take it out, does it affect? As a matter of fact, if I take it out, let's check the AIC. So now the AIC is 46 if I keep everything. Now let me come here. Now I've taken those, I've taken BMI and the location out, and now I've fitted this model. It didn't affect the significance of any of the variables, and it even improved the AIC from the AIC of the previous one was 46, and now the AIC is 44. So it meant that even taking that out improved the model. And at the end of the day, it didn't affect the significance. Imagine if BMI, after taking out, made muscle mass insignificant. It means I have to keep it, even though it is not significant. So these are some of the things you have to be aware, so that it doesn't be like you just feed the machine an information and whatever it gives you, you take everything like that. Sometimes you should have control. That's why those of you who use ChatGPT and some of these AI tools, I've heard a lot of people having very bad comment about this AI tool. But the truth is this: it makes you work smart. The keyboard, Mendeley for referencing, keyboard for paraphrasing, summarizing, and all those things, AI detection and everything. It makes your life easier. You just have to know how to use them. Okay, so this means that once you get output, it means originally BMI and rural the location was part of the best influential variables after we did the lasso. Okay, and where we have missing values here, it meant we should take them out. They are not important and on the contributing possibility to multicollinearity. But we noticed that the ones that are not important, okay, that are not significant, take them. Even though it's important, it was an influential variable according to Lasso. It is not significant. So why should you have it? So when I take BMI out, but rather affect the significance of other predictors, then in that case, I should keep it, even though it's not significant. Okay, because in that case, it meant it might be a moderator. Okay, it might be a moderator, or it could be a mediator. It could be a mediator if after taking it out, it causes a certain variable that was already or previously significant to be insignificant. Then it could have been a potential moderator, and you have to keep it. You don't have to take it away. Sorry, a potential mediator, and you don't have to take it away. And now you notice that if I take BMI out, it doesn't make the model any better. Okay, because the AIC gets improved. And in that case, it means that I can't say it's a moderator. We know a moderator can either increase or decrease the strength of association. But in this case, it's not helping. Okay, so after taking it out, AIC is still improved. And all the segment, look at this. Muscle mass was originally after taking BMI out, muscle mass had 3 asterisks. This 3 asterisks tells the degree of significance. So, but when BMI was in the model, the asterisk was just 2. So it meant taking it out. The reason why it has improved the model was because this BMI was reducing the degree of significance of muscle mass. And I believe it's because they have high correlation among them. So I needed to take it out. All right. So that is it. So it meant you can also use BIC to check. So this is the full lasso model. When I had not taken BMI and the location out, the AIC was 46. After taking it out, the AIC was 44. If you look at the BIC, it was 69. And after taking those 2 variables out, the BIC was 59. So you can use either AIC or BIC to make as a model selection criteria. All right. Okay. So now I'm calling this the model that I've taken BMI, the lasso model after taking BMI and the location, which now we have 3 significant variables. The mass, so it meant muscle mass, the size of the wound, and the wound length. These are the complete, or these are the significant predictors among all the predictors that we considered at the beginning of the study. that we believe with just these three information, you should be able to know the type of weapon. Hello, please can you mute? Please can you mute yourself, please? Hello, please can you mute? Okay, all right. Oh, there's still a background. Please, we're almost there. Can you mute the? Hello. Okay, fine. All right then. So it meant that okay, that's fine. Okay, so we are almost there. So here, the model where we've the model based on the lasso selection, where we've taken BMI and okay. So the model based on the lasso regression, where we've taken away BMI and the location, we are now calling it as the best logistic model. Okay, and that's the best logistic model. And in R, there's a certain package called R companion. It helps you to estimate something called pseudo R squared. Remember that if the dependent variable is continuous, the R square is called coefficient of determination. And in that case, it's not pseudo. But when it's categorical, we also have a way of quantifying R square, but we call it pseudo because it's not a classical R square. And what does this R square tells us? So R square is also a way of assessing the goodness of fit. So this is why I was saying that imagine when you had fitted your data points were just, let's say, 50, and you cannot split your data into training and testing because it's too small. Okay. Okay. When it happens that way, you can, instead of quantifying accuracy, because in this case, you cannot quantify accuracy because the data is too small, then you still have to get a good sense of how good the model was. Then you can now estimate the R square. And remember that for the pseudo R square, in the case of logistic regression, there are three different R squares. But I mostly prefer the Nagelker's R square because it's often the Nagelker's or the McFadden is good, but you can see that some R squares underestimate it. This one, the Cox and Snell is never used or never preferred. So this one is telling us that the model, and what does R square tells? R square tells the proportion of variability in the outcome that was explained by your predictors or the model you fitted. And remember, the higher is something bounded between 0 and 1, and the higher the value or the closer it is to 1, the better the model. Okay, so this one is telling us that our model was able to explain about 89% of the variability, okay, in the outcome variable. And because this R square is high, I believe that the accuracy of my model will be high. Okay, so bear in mind that if your data points are too small, you don't need to split the data into training and testing. In that case, you can still use the R square to assess how good the model is. And bear in mind, if the value is around 0.5, in the neighborhood of 0.5, let's say 0.5, 0.7, 0.6, it's still good enough. But when it's like 0.1, 0.2, 0.3, then there's a problem. It just meant that maybe certain variables needs to be taken out, or you didn't use the best feature selection methods to get the best subset. Are we okay? And after fitting a logistic model, the next thing we often do is call who is doing that? Eric, I think you are okay. So after fitting the model, can this be taken up? Okay, fine. So after fitting the logistic model, the next is to estimate something you call odds ratios. Okay, so the logistic model we fitted in R, we can, okay, this is the best model. So for the best model, we can actually use summary of that, and it will tell us. I don't know why this is here, this red thing, but sorry for that. I think someone accidentally did that. So you can use summary to summarize the output, and you can also use coefficient. Okay, like you can use coefficient, COEF coefficient around the model, and that will extract just the coefficient. Okay. Remember that when you fit a logistic model, the coefficients you are seeing are called the log odds coefficients. At this stage, they are not odds ratios. Okay. It only becomes odds ratios when you take exponent of this coefficient. If this coefficient, you take exponent of them. Sorry. When you take exponents, of them, then we have the coefficient now becomes odds ratios. And odds ratios is so nice to interpret. Okay, it's because in that case, sorry. Oh, yeah. So for odds ratios, interpretability is very powerful. So this gives you odds ratios. So odds ratios are obtained after you take the exponent. So it meant if you want to interpret muscle mass, then this is the odds ratio and so on and so forth. Fine. But there's a package to do that for you without having to do this manually. And it will even give you the confidence interval, the p-values and everything. Okay. So I don't know if this thing can be taken away, that this red pen, but because of time, I'll just proceed. I don't know. Okay, let me see. Eraser. Okay, nice. Okay, fine, perfect. Okay, so I think I'm good. All right then. So okay. So now, so there's this package called epi display. Okay. And have you noticed that I can use the package name and bring two column and specify the function I was using. And that is the same thing as if I had just used, so for instance, if I run this, I'll get the output. It is similar as if I had just used library, if I just use um, if I just use library in bracket, the epi display, if I load this, in that case, I don't need to bring, I just need to specify the logistic display without the name of the package and the column, and that will give me the results as well. Okay, so that is just for you to have a fair idea about. So it meant because at this point I'm just using this function once, so I didn't have to necessarily load it. But even if I load it, that's not a problem. So in that case, if I'm using it just once, I can just bring the package name and the column, and that will also do the job for me. At this stage, this function gives you two important type of odds ratios. It gives you the crude odds ratios and adjusted odds ratios. Those of you who do, especially those in epidemiology, or yeah, I mean, most publications or journal will expect you to report on both the crude and adjusted. Even if you are not into those areas and you are only interested in the adjusted, I think it's important to bring the crude as well. Now, what are the difference between the adjusted and the crude? So the adjusted is, so remember these coefficients, the log odds coefficients are these ones, okay? And after taking exponent, I get the what? I get the adjusted odds ratios. The unadjusted odds ratios or the crude odds ratios is when you had fitted the logistic model. If you had considered only muscle mass without any other thing, then the coefficient you get will be the crude coefficient for muscle mass. So it meant that the crude estimates are when you consider that particular variable alone in the model without anything. Okay. And the reason is that there are instances where the adjusted model, the predictors, the adjusted coefficient was not significant, but the crude was significant. So in that case, at least you can talk about the crude. Okay. But remember that if adjusted is significant, the crude is irrelevant. Okay. The adjusted estimate, once it's significant, is what you should report on. You only report on the crude if the adjusted is not significant. Now, how do we interpret odds ratios? Of course, you can always go to ChatGPT or Google search, but so for instance, if I want to now three predictors were significant. Okay. Now muscle mass, the adjusted, I'll report on adjusted. So that, and bear in mind that it brings two p-values, one from the Wiles test and one from likelihood ratio. I mostly prefer using the likelihood ratio p-values. So it meant that when you are summarizing these outputs in let's say in your publications, you just report on one of the p-values. So just specify p-value and indicate these ones, and don't use the Wiles statistic. Fine. If you use it, it's not a problem, but I prefer the likelihood ratio. Fine. So if odds ratio is the reference is if odds ratio is greater than 1, it means that variable is what more likely. If it is less than 1, it means that variable is less likely to with respect to the outcome. What I just said is just an arbitrary statement. Now let me make it more practical. Now remember that 9 was kept as reference. So it meant every interpretation we are doing will be spared. So this is to say that if it is continuous, how we interpret this is different from when the variable is what? Categorical. And you know this, you all know that in regression analysis, how we interpret categorical variables is different from continuous. For if the dependent variable was continuous outcome, then for continuous variable, we'll be interpreting it as a unit change in that, let's say if the predictor is continuous, they will say a unit change in that predictor will either increase or decrease what? The outcome variable by the regression coefficient, right? Well, if increase or decrease if it's plus or minus. But when it's categorical, when it's logistic model, the odds ratios are interpreted differently. So let's imagine if there was a variable called sex, and let's say females were kept as reference, and let's say this was the odds ratio for males. Okay, if it is less than 1, you can report on the deficit. Deficit means that here the value is 0.3. I could say that, let's assume this was gender and it was males relative to females. Then I will say that males are 0.63 times less likely to what? To use SPA or to use SPA compared to females. But even that interpretation does not really make sense. So instead of that, instead of saying 0.3 times less likely, I can report rather on the deficit. 0.3, the deficit from 1 is basically 27%, right? So I can say males are approximately, let's say, 27% less likely to use a weapon. Okay, then that one will make more sense in terms of that one will make more interpretability sense than saying 0.6 times less likely, even though that is also correct. And if the value is, let's say, 1.7 for, let's say, males, I would have said males are 1.7 times more likely to use, let's say, a SPA relative to females in that case. Okay, that doesn't apply here, but I'm just giving a brief interpretation. But instead of saying 1.7 times less likely, in this case, 1.7 times, it's fine if it is greater than 1, but one could also say that rather report on the excess. So if it is less than 1, report on the deficit. If it is more than 1, report on the excess. What is the excess? The excess is 0.71. That is over 70% or 71%. So I can rather say that males are 71% more likely to use a SPA than females. That one would make more sense than saying 1.7. But if I should run this off to 2, you know, this one to the nearest whole number is 2. In that case, I can say males are 2 times more likely to use SPA compared to females. That one, it makes sense if I don't report on the SS, then I report on the exact value. Okay, so technically, the exact value, you would just say that if it is any value, whether less or greater, it is that value times more or less likely. Okay, if the value is less than 1, it is less likely. If it's greater than 1, more likely. But remember that sometimes reporting on the excess or the deficit, depending on whether it's less or greater than 1, makes more interpretability sense than using the actual magnitude, isn't it? So it's just something I thought I should say. But when it is continuous, how we interpret it is very beautiful. But most people don't know the best way to interpret it this way. So in this case, muscle mass, the adjusted ratio is 0.63, okay? 0.63. I'm going to report on the deficit, but look at how I'm going to say it. So the deficit is still like 27% or 26% or something. So what I'll say is that higher values of muscle mass is associated with a 27% decrease in chance of using the weapon being SPA. Maybe I've made it a bit complex. Let me make it smaller. So what I'm saying is that we believe that it meant that as people, those whose muscle mass are higher, okay, would have a lower chance of, or the probability or the chance of them using a SPA would be lower than if it was their weapon, their size was lower. But to say this to make interpretability sense, and I'm reporting on the deficit because it's less than 1, I'm saying that higher values of muscle mass are associated with a 27% decrease in the chance of the weapon being SPA. I mean, so that is also another way to interpret that. So yeah, and then the wound length. Okay, so the wound length, sorry, the wound size. Oh, the person did it again. Sorry about that. So let me, okay, that's fine. Okay, so the wound, okay, so let me erase this one. Let me cancel that. Okay, so the wound length, let's say the odds ratio is 0.7 0.495 or whatever. So let's say 0.5. Yeah. So so in this case, instead of saying that um a unit increase in the wood length will increase the chance of the weapon being a spear by 0.4 times, which doesn't make, I mean, even though it's correct, but it's not, it doesn't make, always your interpretation should make sense to clinicians or to the target population of interest. It should make sense. So in this case, I'm going to report on the deficit. Okay, so the deficit, if it's 50%, the deficit is 50%, right? If it's 0.49, let's say, okay, let me say 51% deficit. So I'll rather say that higher size or higher wound size is associated with a 51% let me say, let me repeat it. Higher wound size is associated with a 51% less chance that the weapon used was a spear. Okay. Now let's look at when I'm interpreting wound length when it is 1.7. Okay, so 1.7, I'm going to report on the SS, which is 70%, not the deficit, because this one is greater than 1. So for the SS, I will say that higher length, higher values of the weapon length, okay, or higher weapon length, or I will say as the weapon length increases, or let me say higher weapon length is associated with a 71 percent increase in the chance of the weapon used being a spear. So this one, if you think about it, it meant that the longer the weapon, the higher the chance that the weapon is a spear, and the shorter the weapon, the lower the chance that the weapon is a knife. And I think it makes sense. So this is just, I was just trying to explain what illustration basically are, how you should interpret it in the case of it being continuous or okay, so someone is asking why spear used in the interpretation but not knife. Is because when we were fitting the model, we set the knife as a reference category. So it meant that the one you set as a reference category, we are not reporting on it. So it meant everything we are reporting is the spear relative to the knife. And I think you embrace it when we get to the prediction shortly. Okay, so now we fitted the model based on the training, and this is the interpretation. And one interesting thing about odds ratio is that it helps you to assess what variable is the most important. Sorry. So now you notice that the wood length has the highest odds ratio. Since it has the highest odds ratio, it meant the wood length is the most important predictor of the weapon type, followed by the muscle mass, okay, and then followed by the wound size. And the interesting thing is that you can actually use in R, there is a certain function, I think it's called variable imports. Okay, I think when I get down, I think I did it down there. We will see that I need to install a package for that. So there's a certain function, but you can tell it from here that the higher so it means odds ratios are used for two things. It is used to, first of all, quantify the strength of association and also to determine the direction of association. The direction in the sense that it tells us to know whether individuals with those characteristics are less likely or more likely. So that's the direction. And the magnitude is that it tells you whether you are 2 times more likely, whether you are 70% more likely, 70% less likely, that kind of thing. So it tells you both the magnitude and the direction of association. All right. So to know that this package is very powerful. For the crude, I said the crude is when you had considered only, let's say, muscle mass in the model without adjusting for anything. So the crude is another name for the crude odds ratio is unadjusted odds ratio. All right. So and the person who asked the question on why we are reporting on the spear is, like I said, is because we kept knife as reference. If we had kept the spear as reference, then our interpretation would be weapon would be the knife relative to the spear. Okay, so don't forget that. All right, so if you do the logistic regression model with just the muscle mass, and you use the same function to calculate the odds ratio, it will give you exactly, this odds ratio is exactly the crude. Okay, so that's what we mean by the crude. The crude is just when you consider only that predictor in the model and not adjusting for anything. And you notice that in this case, the p-values you are seeing here is p-value corresponding to the adjusted odds ratio. So imagine if you wanted to know the p-values for the crude odds ratio, you could also do it like separate like this. And in that case, you'll be able to see the p-value corresponding to this as well. All right. But mostly it's because the adjusted is what is important. So we just have to have the p-value corresponding to that. And remember that you don't even need a p-value to conclude whether a certain odds ratio was significant or not. If the odds ratio does not contain 1, so here you can see that 1 cannot be found in the center of this range in the confidence interval, then it means that variable is significant. This one is 0.3 and 0.7. You can't find 1 in there. This one, it is 1.3 and 2 point something. The moment if this one had been 0.3 and the upper one here had been 1 point anything, 1 can be found in the middle. That means that that variable, the p-value wouldn't have been significant. Okay, so that's one thing I just want us to know, that you can actually conclude on significance of odds ratios based on the confidence interval without even making use of p-values. So that is that. So the next step, or the final step, is that after we fitted this model based on the training data, we are now going to cross-validate it. To cross-validate, it means that we are now going to what? Make predictions based on the fitted model using the predictor information, this one that were significant. So it means for each individual in the testing data set, we are now going to make use of these predictor information and predict the type of weapon that was used to stab them, and check the proportion of times we're able to make good prediction. Okay, so it meant that anyone who is into betting, I'm not going to advise betting, but imagine if you were looking at a football match and maybe they can either win, draw, or lose. Let's assume you can either win or draw. Okay, and in this case, you have a data of all cases. So it meant if you're a statistician, you can actually look at a particular team, look at the number of players that were used, other predictors, and then look at in that particular match, when they went home or away or whichever, did they win or lose? You have such a data. That's an empirical data. With that data, you can now make predictions for a new game that is yet to be played. And then you'll be able to quantify the magnitude of prediction. Okay. So everything we are doing, just understand that anytime the outcome is a classification outcome, whether win or lose, whether dead or alive, whether a weapon being a knife or a spear, whether and it shouldn't necessarily just be 2 categories. Even if it's more than 2, then you use the same analysis you do multinomial logistics. Okay, and everything would the interpretation, everything will be the same. Okay, so to do model cross-validation, these are some important packages you need to install. And because of time, I'll rush this through. So it meant that this was the best model we've already found. Okay, so we can also use a certain package called Carat. With that package, you can actually also predict, you can also fit different models. The Carat package is very important. It's very useful in the sense that in the Carat package, if I bring a question mark and specify the name of the function, it will help me to know what is in there. Okay, so this one, it doesn't give us more details at this stage. But the Carat package, you can use it to even fit machine learning models. So if you are doing classification tree, you can specify if it is, let's say, gradient boosting machines, which is a classification a machine learning model. You can specify it here. If it is a classification tree, you specify if it's you specify if it's a tree model, you specify tree or something. And if it is any model you want, you just have to specify the method here, and it will do it for you. So that's the advantage of using the Carat package. Fine. Anyway, so if just that the Carat package, the beauty is that if you fit the model based on the Carat package, you also are able to see the accuracy automatically. So this one is telling me that the model is 97 accurate. So it meant when we're comparing when we predicted for the data we left out, the model was about 97% of the time was able to make correct classification. As a matter of fact, so this is based on, bear in mind that at this stage, this is based on we've just trained the model, right? So this accuracy we are seeing here has nothing to do with the testing data set. This accuracy we are seeing here is like, after it fitted the model, it decided, based on the training data, decided to predict the outcome of the training data set and looked at the proportion of time the model was able to make correct classification. So it meant this is not the accuracy we are interested in. So for the accuracy we are interested in, we need to now do it based on the data we left out. Because the truth is this: if I have used a certain data to fit a model, and now I'm using that fitted model to make predictions for individuals in that same training data set, that's a biased conclusion, because in this case it looks like, because it's the same data that was used to fit the model, if you are now making predictions based on the same set of individuals, you are certainly making a biased conclusion. So we want to now fit a model based on the training data set, and then use a different model that was not a different data that was not used in fitting the model at all, and see if we can make correct predictions. So, and that is what we are doing here. So here, we have a function called predict. We specify the name of the model, and here we specify the test data. So now it's going to predict for just the outcome variable of the test data, and based on the predictor information from the test the individuals or the cases in the test data set. All right. So after doing this, it tells us that the model is 98% accurate. And look at this. This reference, this one was situation in the testing data set. This cross tabulation tells about 131 instances. The weapon was indeed a 9, and the model was able to conclude that it was a 9. And in one instance, the weapon was a spear, but the model said it was a 9. In only one instance, the weapon was also a 9, but the model said it was a spear after prediction. And about 70% of the time, the weapon used was what? About 7%, 17%, about 17 instances. The weapon was a spear, and the model concluded or predicted it to be a spear. So if I want to calculate the proportion of correct classification, I just have to add 131 plus 17 and divide by the total instances. And that will give me the proportion of times we're able to make correct classification. And that is exactly what this is. So it meant that if I should consider 131 divided plus 17, these were the instances we made correct classification, right? And if I divide by the overall total, so the overall total, I have 131 plus 17 plus 1 plus 1. So that will, sorry. What did I do? Okay, so that will give us 98.6. And that is exactly what this gives us. And the beauty about this is that it also gives you confidence interval, so that you say that the accuracy is bounded between 95% and 99%. Okay, so but it's to say the model was about 98% accurate. And that tells you how powerful the model we fitted was. Now, there are other things you can do. You can also look at the ROC curve, the AUC. So there are other statistics that you can use to assess business of fit. But remember that since it's a classification tree, a classification problem, okay, and then we are trying to use model cross-validation, because model cross-validation using the tested data set gives us more confidence about the model we fitted. But again, I said that if your data points are too small, then splitting your data into training and testing might not be ideal. In that case, you can fit the data based on, if let's say your data is just 30 and you are doing logistic, and you want to split it again into training and testing, that will be a problem. It meant you will end up using just 20 of the individuals to fit the model and only 10. And what makes you think that 20 is going to give us any good model? Okay, so when your data points are just too small, then there's no need to split the data, split it into testing and training. Then you can use the full data to fit the model, but you can now calculate the pseudo R squared, the negative pseudo R squared, which we've already demonstrated how to do that. And you can also look at calculating the area under the curve, okay? Or you can look at the Gini coefficient, which is a function of the area under the curve. And you can also look at something called Kolmogorov-Smirnov statistic. And that this statistic is also bounded between 0 and 1. And the closer it is to 1, the better the model. So these are also goodness of fit, but they don't talk about accuracy. They just means that the model is a good model or it's a good fit. But if you want to talk about accuracy, then you should be able to predict the proportion of times you're able to make correct classification. And you can only do that when you have a large amount of data set in the training, and then you can use it to now predict for the testing and make that comparison. Are we okay? Now, after doing this, now the next thing is to now make specific, because don't forget in the whole forensic problem, let's remind ourselves here. So we said that we found a certain victim. The victim has 4 wounds, okay, with different wound sizes, and we want to be able to tell for each wound whether it was a knife or a spear that was used. Okay, and this is a new individual who has nothing to do with the data we used. That individual has nothing to do with the data we used. So it meant that after we fit a model, what makes the model fitting important is that we use an empirical data to fit the model. So after doing that, it means we can now make specific prediction based on entirely new information. Just as the testing data set was entirely new to the model, and we're able to know that the model is 98% accurate in predicting the type of weapon, then it means we should now be able to make very good prediction with confidence about which weapon was used to cause or inflict each of the 4 wounds. Okay. And now we know there are 3 important predictors: muscle mass, the size of the wound, and the weapon length. These are the important predictors that once we know is sufficient in order to conclude the weapon type. And that is what the logistic regression told us. Okay, fine. So to do that, so that's basically what you are trying to do. Okay, that's basically what you are trying to do. And in R, or in not necessarily R, there's a particular function or formula to calculate the type of weapon. So if your variable is, even if so here we are predicting the weapon type to be equal to to be a sphere relative to what? Relative to 9. That's exactly what we are doing here. Okay, so here we are looking at the weapon type being a sphere relative to a 9. So that if the probability of it being a sphere is low, then the probability of it being a 9 is high. That's basically what we mean. All right, and this is the formula. This is the formula. So it meant that if you look at the formula, this exponent, the numerator here was the regression model we fitted, and you are taking exponent of that and 1 plus exponent of that. Okay, so that is the simple formula to now calculate remember that the logistic model was like log of p divided by 1 minus p, okay, equals that b naught plus b1 x1 plus b2 x2 plus in that fashion. Okay, so imagine this was the original. That's why when you fit the logistic, the coefficients are called the log odds. And remember that this p over 1 minus p is called the odds ratio. So this one is the same thing as log of the odds ratio. That is why if I want to get the odds ratio, I just have to take exponent of both sides. And in that case, it will be odds ratio is equal to exponent of what is here. Okay. Yeah. So mathematics is beautiful. I mean, these formulas, most people don't understand how these manipulations are done, but that's what I just did. So here, the logistic model is just predicting the log of the odds ratio. Just that this odds ratio is basically p, that's the probability divided by 1 minus p. Okay, so that is basically what that is doing. But what is inside here is called the odds ratio. Okay, or in this case, you can just say the odds, so that we are looking at predicting the log of the odds. So it meant these coefficients are log odds coefficients. So that is why if you want odds ratio, then we have to take exponent. Okay, the odds are just like odds ratio. And if you want the odds ratio, then we take the exponent, and then the exponent that we get are going to be the odds ratios. Okay, so that's basically what the odds ratio does. Okay, fine. So these coefficients are the log odds. Okay, these are the log odds, and when you take exponent, then you get the odds ratio. So I basically created my own function. So if you wanted to do this in SPSS does not have any function, inbuilt function to calculate this probability for you. So that is why most people use SPSS, even Minitab, Stata, after they use logistic to identify predictors, significant predictors, they can't do anything further. They cannot make specific predictions about the probabilities. Okay, it's because the functions do not have inbuilt functions to do that for you. But here, I'm creating my own functions to do that based on the results I have. So that is why you should learn how to create your own functions, because there are many instances it becomes imperative. So here I've created my own function. How to create your own function? If you go to the YouTube channel, like I said, there are specific videos on how to create your own function from scratch. It's very simple. Please get time and watch them. Okay, so I've just created this formula. You should be able to create a function for any formula. And I've done exactly that. Okay, fine. So that's what I've done. So that at the end of the day, I'm extracting. So this is the model. And I've extracted the coefficient and down. It meant that all I need to know is that if I specify a particular muscle mass and a particular wound size and a particular wound length, it should tell me the exact probability of it being a spear relative to a knife. So now this function that I've created, let's test it. So for instance, if I should copy this one and create a new Excel, yeah. So this one is like, I want to make a prediction. I want to predict whether the weapon was a knife or a spear. If the perpetrator has a muscle mass of 70 and the wound length on the victim was 10 and the weapon that was used was 70, okay, in 70 centimeters in size, what is the probability that it was a spear relative to a knife? So if I find this, the probability that it was a spear is 0.09. That is low. Then it means that the probability that it was a knife is 1 minus that, and that is 90%. So there's a 90% chance that if these are the information that we recorded, then certainly that weapon was a knife. And that is the beauty about these predictions. So you can now make these specific predictions based on the predictor information here. All right. So that is basically what we did. Yeah. So this is the function I was talking about. Okay. Okay. So it's the best logistic model. Let me come here. Just a minute. Okay. When I used, okay. What happened? Okay. 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 Fine. So now if I should come here, remember that when we did the odds ratios, okay, let me just copy this bit. So in R, there's something called variable importance. There is also a way to quantify importance. I told you the odds ratios help us to know which variable was among the significant ones, which one was more important in that fashion. So here we said the weapon length had the highest odds ratio. So because of that, it means that it's the most important predictor. And look at this. When you use variable importance, which is a function in R, it tells us that weapon length was the best overall. Like, forget about the value here. The value here is not what is important, but it's about it did some ranking. Then this is trying to say that had the highest ranking among the three other predictors. So if you look at this one, it meant that the weapon length was the most important, and it reflects in the odds ratio that it had the highest odds ratio. And then if you look at the muscle mass was the next important one, and you look at the muscle mass was the one with the next second highest odds ratio. And the wound size was the least. It had the least odds ratio, and that's why it is the least important among these ones. So this is also a way of knowing knowing that from logistic perspective or from the odds ratios, you can tell among the predictors which one is the most important, so that when you are making interpretation, you can say all those things with confidence. Are we okay? All right. So now we are making the prediction. So if you look at the forensic problem, now we have 4 wounds, and these are the measurements. So all we need to do is that, just like here, when we're making the when we're testing where is it? When I was testing the function you created, I just have to specify the wound size and then the length of the weapon and the muscle mass of the perpetrator, and it will predict the exact probability that it was a spear relative to a knife. If I want to know the probability that it was a knife, it is just 1 minus the probability that it was a spear, because the two are complementary. And in statistics, if two events are complementary, then the probability of the other one is just 1 minus the probability of the occurrence of the other. Okay, so that's straightforward. Okay, so so the person was asking questions why we were always reporting relative. We're talking about, the odds ratios were emphasizing on the sphere. It was because we made a sphere reference. We made 9 reference, so everything was on the sphere. But don't forget sphere relative to 9. Okay, so it meant that even in this interpretation, I should say that higher values of weapon length is associated with a 71% increase in the chance that the weapon was a spear relative to 9. Don't forget to bring relative to 9 so that it doesn't look like we are placing all the emphasis on the spear, because indeed the person who asked the question asked a legit question. You have to make sure you bring relative to the 9 so that it doesn't look like it is all about the spear. Okay, even though when you set 9 as reference, it's about the spear, but you are making it relative to that. All right. Okay, so all I've done now is that we said the wound length was 26, 28, 30, and 32. And then because we don't know, remember in the CCT, in the forensic case, we said we don't know the muscle mass, but we believe that the muscle mass will be between 70 and 80, according to the forensic team. So all I did was I checked just a few values ranging between 70 to 80. And then in terms of the weapon length, they said they don't know the exact weapon length, but it's estimated to be between 90 and 105. So I also decided to choose possible values, maybe 4 possible values. It doesn't have to be 4, it can be more, but I'm just choosing possible values ranging between 90 and 105. So I chose 90, 95, 100, and 105. And so I'm going to make prediction looking at possible combination of these. So it means I have to make prediction assuming the wound length is 26, when the weapon length is 90, 95, 100, and this, and also when the muscle mass is 70, 75, that and that. How do I do this? Using something called a loop. So this is why when you learn how to create function, you hear things about for loops. With the loop, you are able to now do all these combinations at the same time. So at the end of the day, I'll be able to now, so for instance, so at each wound size, now I have a particular data which is looking at the predicted values. Okay, so just go to my YouTube channel on so if you go to my YouTube channel, so there's a whole video on loops and apply functions, and you understand how it works. It's quite simple. All right. So instead of now doing this one at a time, instead of now looking at the wound length being 26, weapon length being 90, and muscle being 70, and now come to 26, 95, 73, one at a time, I will use loop, and it will do that for me in a jiffy. And that's exactly what I did. It does it straightforward, and it produces all the results. And there's a way of saving all your results. Okay, so that makes it easier. So here you notice that I have prediction for the prediction being a spear, the wound being caused by a spear, and I also have it being caused by a knife. And notice that once I predict the probability that it's a spear, and I want to predict the probability that it's a knife, I just have to subtract it from 1, and that will give the probability that it was a knife. Okay, so that's fine. So this course is just telling the results. So it's telling different muscle masses, and then it's telling the weapon length that was used and the corresponding probabilities at each instance. Okay, so here it tells me that when a weapon length is 90, for the wound length of 26, when the weapon length is 90, this is the probability of it being a spear at different values of muscle mass. Okay, so that's what I've done, and I can visualize this graphically, and that's exactly what I've done here. So you can take time when you get the course, take time and replicate this, and you understand, because we've spent so much time. So I just have to wrap it up here. So here, these are the graphs I've produced, and let's try and understand at least one of the graphs. So what this is trying to say is that as the length, so the y-axis here is weapon length, okay, and I've done it at each of the possible muscle masses, and what you are seeing, the red, yellow, green, orange is corresponding to the wound size. Okay, so here anytime you see blue, it means the wound size was the 26. So these were the 4 wounds on the individual, and you want to make predictions on whether this wound was caused by a knife or a spear. But now look at something. So let me come down. Let me interpret for let's say this one. So this one is telling me that first of all, irrespective of the muscle mass, you notice that as the wound length or the length of the wound increases, the probability that the weapon was a spear relative to it being a knife, or the weapon was a spear, increases as well, as you can see. And it makes sense because we know that spears are naturally supposed to be longer than a knife, and it makes sense. Like those spears, those who have been watching Game of Thrones and those movies, you see that spears are very long. They are those long ones where you have a bow, something to like forgetting the name. I don't know whether it's armor or whatever. Something that you use it to protect yourself, and the spear will be holding them like that. I mean, those times they use it a lot for war. All right, so it makes statistical sense why, as the weapon length increases, then the probability of the weapon being a spear also increases. But there's also another thing you should note here. You notice that as muscle mass changes, the dynamics changes. The dynamics are changing. Okay, the dynamics changes as a function of different values of muscle mass. So here, technically, irrespective of the muscle mass, you notice that whenever the weapon, the wound length, okay, is lower or smaller, in this case, it appears that the probability of it being a spear was high. I think a possible reason for this, okay, don't forget these are simulations, so it might not necessarily make a lot of meaningful sense, but it still makes sense in the sense that the spears, for a spear, the tip is very, if you look at the shape of the weapon. So this is a spear. Look at the tip. It's very, very small in terms of the tip. But a knife, most of the a knife can be very broad, So sometimes someone, and the way one can throw their hands with a knife, it can cause more devastation if you think about it, devastating effect. But of course, with the spear, if you've been watching those movies, sometimes you can only use it to hurt someone at one particular point in time, at just one body part. But for a knife, you can actually cut through someone. And that's why sometimes maybe the wound created by a knife can be much more worse than a spear, because a spear mostly targets just one particular part, but a knife can cut through different areas or surface areas of the individual. And so I'm just trying to make sense out of the impossible. Yeah. So on this note, I would end here, and just to so the whole take-home message is that we just wanted to know how to use logistic regression for classification problem. And what we've learned, you can adopt it if the dependent variable was either dead or alive instances. So that is like a survivor data, or if the dependent variable was about whether an individual is infected or uninfected. Okay, and it's not just two categories. You can consider it when the categories are more than two. Just that in that case, you not use the GLM function. You use a certain function called multinom. That's for multinomial logistic. It's in R, and the package for that is called NNet. NNet is like it's a neural. It makes use of some neural network method. I mean procedure, but that's the best package for logistic, a multinomial logistic, and you can always go online and get that. You can always go to Google and type how to remember. Once you import data into R, everything else you can make use of Google. So for instance, you know how to import data. Now you want to do, let's say, a logistic regression. Imagine if you didn't know anything I've done today. You just go to how to do logistic regression. You get a lot of online blogs. People have done these things. Like for instance, this one, I can put it on my website. And once I put it on my website, you'll be able to, yeah. So if you want to send an email, once you go to Google, you type my name. Okay. Once you go to Google and you type my name, okay, I'm just doing it so that I don't have to necessarily send it to everyone. So once you go to Google and type my name, the first link you see here is my Oxford University website. If you click there, you see my email, either my Oxford email or my Gmail. Okay, and so you can send me the email via any of them. Just send me the email either via the Gmail or my Oxford email. Probably I'll say my Gmail if that makes it easier. But any of them, and then you'll be able to get access to. Yeah, so just go to Google, type my name, and yeah. So once you type my name, I think you get access to everything about me anyway. So everything, like everything. Yeah. So but the first link will take you to that. Okay, so without wasting time, I will end here, and don't forget to subscribe to the YouTube channel. The videos, everything we've done will be uploaded on your YouTube channel. And for the codes, we'll think about the best way for everyone to get it. But I'm sure I'll put it on my Piazza platform, this one, the Piazza platform, where you're able to access all these. But in order to be able to access this, I think once you send me the email for me to add you to the Piazza website, you'll be able to download everything. Okay. So without wasting time, I'll end here and I'll take questions. Thank you very much.